Hello, and thanks for tuning in to the Gear Enterprise Project. Our advisor is Brett Hamlin. My name is Morgan Bialek.
My name is Nolan Rubel.
My name is Cora Jarman.
My name is Jake Abbott.
And we're going to talk to you about our project this semester, the Copper Harbor Rescue Device.
So the existing device for extracting injured riders out of the bike trails of Copper Harbor is slow, unstable, and requires a large rescue team. It is a one-wheeled structure where the rescuers walk from the trailhead to the injured rider, pick them up, place them on the unstable structure, and then balance the rider on the stretcher as they walk back out of the trail. Our solution is a more stable device, which is towable and requires a smaller team. So the rescuers can tow the empty device behind the bike from the trailhead to the injured rider, then load them onto the wheeled device while it's stable and freestanding, and then 1 to 2 people can bring the rider out of the forest.
I'm going to talk to you a little bit about the stages of our prototypes. We initially started with a wheelchair-like device because we figured that injured people move around in wheelchairs, initially. So we wanted to kind of base our design off of that. So we built a CAD model and a wooden model to kind of give scale and concept. And from there, we added handles. And during this phase, we actually discovered a bike cargo trailer that kind of served as a turning point in our design phase. And we from there moved forward with a 3-wheel design that you can see in the bottom right corner. And this was kind of aiming for a more stable design, over 2-wheel design. So with that 3-wheel design, we decided to add a suspension fork to smooth out the ride on the injured rider and reduce shock. And with this fork, we actually raised the angle that we had initially designed, and this can account for a safer downhill travel. Rather than the cart leaning steep forward, this angle will allow for a safer riding position. We have an unlocking front wheel, which will allow the device to take tight turns, and also a detachable transport arm that takes the place of the wheel, and that can connect to a rescuer's bike. So our device can be biked in, drastically cutting rescue times. And then we also tapered the footrests to save weight and reduce the footprint. We decided to go with aluminum bar stock, 1 inch by 1 inch with an 1/8 inch wall thickness, because it offered good strength and also a low cost. And it also kept the weight down to maintain easy maneuverability. We went with the 29-inch fork and wheel, again, to increase ground clearance and rollover and lift that front end up a little bit for a safer downhill experience. And then we also added toggle clamps to the seat to clamp it to the frame, and each one of those has a 700-pound capacity. So the rider will not be ejected from the vehicle upon any bumps.
The next step was to design a solution which would allow the integration of the front fork into the existing frame design. In order to do this, a bearing holding headset was modeled to be CNC'd out of a 2x2x4 60/61 aluminum block so that the flat face could be welded securely to the front of the frame. The design was made to accommodate an integrated headset bearing kit. The use of the bearings allow for free turning of the front wheel during use over rough terrain and through tight, narrow, winding turns. Design verification was conducted on the CAD modeled frame using finite element method analysis. A variety of load cases were tested using Hypermesh OptiStruct FEA software. Stress concentrations were noticed in segments of the product where shoulders of the frame met. Additional support material was added to the frame and iteratively retested in the software for design, which successfully distributed the stresses safely below the yield strength of aluminum.
Moving on to outcomes, we have a fully functioning fabricated chassis that is a strong prototype for further testing and improvements. And for conclusions, our most notable one is that we accomplished our goal of having a stable functioning prototype. This prototype is able to transport a person, which is crucial for full-scale live testing. It's structurally sound and it's able to be towed with a bike front using the front fork. So future recommendations, these are things that we wanted to add to the bike that we've seen are necessary. The first thing would be adding a braking mechanism. This would require a custom lever. And we want to perform testing using a simulated injured rider. So we would take the bike out to the trails and then run through the whole point of injury, getting the bike to the person and then getting that person out. We would record the time, the ease of use, all of those things. Another thing we wanted to add was padding to the seat and then adding them one size fits all leg rest using mesh. Moving on to things that we want to consider. These are things that aren't necessarily necessary, but these are things that we think should be considered. First thing would be lowering the rear axle. This would move the wheels down and allow for the chair to be moved in and out easier. Right now, you would have to lift the chair over the wheel, and lowering the axle would make that process much smoother. And then lastly would be small things like grinding out more welds, coating the metal to prevent rusting and damage, and then what the best storage technique would be out on the trails.